Okay, so I hear a few pencils hitting the ground or the desk. That's good. That means you're done, right? Okay, so find all solutions. Okay, so that means we're going to be writing down answer sets. So I think the first way I showed you how to do this was to draw a picture for this. This is the adjacent, and this is the hypotenuse. So if we draw an adjacent side of 1 and a hypotenuse of 2, if the adjacent side is positive 1, it's got to be right here. If that's 2, we're here. That makes this radical 3. If you want to solve that using the Pythagorean theorem, be my guest. That makes this a 30, 60, 90, okay, which makes that angle pi thirds. Okay, so then that would repeat every time we go around the circle. So that's going to be pi thirds plus 2k pi is how we wrote it, right? Because it says find all of them, so we're going to have answer sets. Okay, is that the end of it, Michael? Oh, it does say degrees. Wow. So this is going to be 60 degrees, so this is going to be 60 degrees plus 360k. We good there? Okay. Is that the only answer set? No, because we can draw that same triangle down here. That same side is 1, a positive 1 because we went to the right. That's a 2. That would be a negative radical 3, not involved in the cosine ratio, so it doesn't matter. If this little angle right here is 60 degrees, that makes this reference angle 60 degrees. So the way we'd figure this out, and if you haven't gotten this straight at this point in the chapter, make sure you keep this in mind. There are all those boxes in each one of the sections that tells you how to solve an equation involving a sine, a cosine, a tangent, or different things like that. In general, if you can draw one of these triangles, we always draw a reference triangle and that reference angle with the x-axis. So let's compare everything with the x-axis. That's a 60-degree angle. That's a 60-degree angle. On the x-axis, this would be 360 degrees going around full circle. Let's back off 60 degrees. So this is going to be 360 minus 60 degrees. So that answer would be 300, and then how often would it repeat? Every 360 degrees. Okay? So there are the two answer sets. There's one answer set, and there's the other one. And those are all of the answers. Your calculator, if you plug that into the calculator, would give you this answer up here. Whoops. You'd have to use your brain to figure out this one down here. Okay? And then you'd have to know how often it repeats and all that sort of stuff. Yes?
What is that symbol on the 360?
This right here?
Yeah.
Just a degree sign.
The letter next to it.
Oh, it's a K. K. K is any integer. Okay, any other questions? Okay, and then we looked at why it works the way it does. So a cosine graph looks something like this. And then we draw that constant. That constant would be 1/2, so 1/2 would be about right here. So it's going to intersect here on the way down, and then on the way down here, and then if we backed up here, it would intersect right there. Those are this answer set right here. 60 degrees on the way down, another 60 degrees coterminal on the way down. That would be 420 or something like that. And then this one here is on the way up. That's the 300 degrees. It repeats every 360 degrees. So there we go. That's a picture of those two equations graphed and where they cross. Any questions there? Okay. All right. Then if you know how to do that, there's not much difference between doing those and doing the problems for 4.3. Okay, there is one small difference. Makes it a little bit more complicated, but we're going to go about it in kind of a systematic way and have this figured out. This technique is one that's used over and over and over again in math. You first probably saw this technique used in Algebra 2. I'm sure you saw it in 1050. You'll see it again if you take 1210 and in 1220. Okay, so here's the equation that we need to solve. Cosine of 2x equals 1/2. Well, normally if there's a 2 and we don't want it, we divide by 2, but you can't do this because it's the argument or part of the argument. The angle was multiplied by 2. Okay? So we're going to solve this by making what we call a substitution. A substitution. Okay, now what a substitution does is it makes something that looks unfamiliar more familiar. It makes it look easier. Okay? So you might remember that you've solved things like this, like maybe you had, let's see, what would you have done in 1050? Solved an equation like, whoops, solved an equation like that. Used use, okay? So we call this a substitution or a change of variables, or most people just call these a U substitution. Again, you use a U substitution to make things look more familiar. So here's what we're going to do. We're going to say, look, I know how to solve a cosine equation, but if there's a double angle in there, if there's a 2x, that makes it more complicated. So this section, again, is called multiple angle equations. There's that multiple in there, that multiple of 2. So what we're going to do is we're going to say U equals 2x. Wherever there's a 2x in the problem, we're going to put a U. So this means we've got cosine of U equals 1/2. Well, doesn't that look familiar? That's exactly like this one up here. So you could draw the pictures and all that sort of stuff, use your calculator, draw the graphs. However you solve it, you're still going to end up with 2 answer sets. So this says answer in degrees, so one of the answer sets is going to be U equals, that's going to be 60 degrees plus 360k, and the other one is going to be U equals 300 plus 360k. I mean, it's that simple. It's exactly like the ones that we just got done solving. Except for the problem wasn't about U's. The problem had X's in it. We did the U substitution to make it look more familiar and to make it easier. Okay, now what do we have to do? Put the answer in terms of X. Change it back. So we need to reverse the substitution at this point. So wherever there's a U, I'm going to change back to X's. So this is going to be 2X equals 60 plus 360k, and this is going to be 2x equals 300 plus 360k. And then from that, I can then solve the equation. So I'm finally to the point where I can solve this by dividing by 2. So we'll go ahead and we'll divide everything by 2. So this means x is equal to 30 degrees plus, well, if I divide everything by 2, this is going to be 180k. And if I do the same thing here, this is going to be 150, because that was a 300, right? 150 plus 180k. So those are all of the answers. It's basically one extra step on top of what you already know how to do. You know how to solve this, not this, so make a substitution, solve the equation you already know how to do, reverse the substitution, and then just divide or multiply whatever it happens to be to get x by itself. So in this case, we've got x equals 30 degrees plus 180k and 150 degrees plus 180k. Any questions there? All right then. I've got a few questions for you then. Why are those the correct answers? One of the answers is 30 degrees, right? Does everybody agree that one answer that would work in that equation is 30 degrees? Plug it in. What happens when you plug it in? Because if you take the cosine of 2 times, we're plugging in 30 degrees. The very first thing we do with 30 degrees is we double it. Well, what do you get when you double 30 degrees? 60 degrees. So this becomes the cosine of 60 degrees. And the cosine of 60 degrees, adjacent side, x-coordinate on the unit circle, is 1/2. It makes the equation true, right? Okay, well, let's do this one. Let's not do 150. Let's plug in a 1 for this. A 1 for k. You can plug in any integer you want, so let's plug in 1. So that's going to be 150 plus 180. 150 plus 180 is 330. Okay? So this was when k is equal to 0. This is when k is equal to 1. So 330 degrees. Let's see if that works. So if I plug that in here, again, the first thing I'm going to do with it is I'm going to multiply it by 2. So this is the cosine of 660, which is coterminal with, subtract 360, that's going to be coterminal with 300. And what's the cosine of 300? Positive 1/2. Okay? So they're answers because when you plug them in, they make the equations true. Okay, so there's no doubt they work, right? Okay, Why do the answers repeat every pi units, or let me change colors since we're on a different one, every pi units or every 180 degrees instead of every 2 pi units or every 360 degrees? Okay, can someone answer that for us? It does, very good. It changes the period. Okay, if you take a look at cosine of x versus cosine of 2x, that changes the period. It increases how fast it's cycling. So, where the normal cosine curve might look like this, our cosine curve, cosine of 2x, is going to produce the same graph in half the time. So it's going to do this. Okay, that's really crappy, but you get the idea, right? Okay, so now let's graph 1/2. Okay, for the black one, it only intersects here and here. Okay, let's just take that side. Look how many times it intersects here. 1, 2, 3, 4. Because it's cycling twice as fast, it's going to produce twice as many answers in the same amount of time. Okay, so does everybody see why it's going to repeat every 180 degrees rather than every 360? Okay. Faster cycling or smaller period. It's producing answers twice as fast. The period is half the size. Okay. Any questions? You're sure? Because if you get this, the rest of this is really pretty easy. Solving these types of equations is a piece of cake. Okay. All right. Let's take a look at the next one then. Okay. I do want to point out that even if you get the general technique, this is a good thing to keep in mind. Okay, regardless of what the instructions are, it's usually a good idea to find all the answers. In other words, write out the answer sets, especially when we get to these multiple angle equations, because some of these you're going to have 12 answers to. Okay, you don't want to run through and risk that if I think my way through this, I can figure out what all of the answers are. If you write down the answer sets and then just plug in different values of k, that's going to be much more useful in the long run. Okay, so find all the answers. In other words, produce answer sets. Okay, and then find ones in the interval that you need. Okay, so write the answers using k, and then plug in values of k that produce answers in the correct interval. You'll see why that's valuable in just a minute. So let's take a look at this problem right here. What are we going to do first? Yeah, substitute for u. We're going to do a u substitution. We're going to make this look a little bit easier. So this is going to be the tangent of u is equal to -1. And then we're thinking, all right, that is a tangent ratio. It's -1. There are two ways I can do that. -1 for an adjacent, 1 for an opposite. Or I could do 1 for an adjacent, -1 for an opposite. Doesn't really matter on tangent, does it? Can anybody tell us why? It doesn't matter which one you do. It repeats every pi, right? Okay, now we do need to answer this one in terms of pi. So this one's going to be, well, let's get this positive answer first, right here. So that's going to be u equals 3 pi fourths plus k pi. Okay, there's the answer set. Is that the answer set we need in terms of the variable that we need? Nope. So we're going to come back here and we're going to replace this. Wherever there's a u, we're going to put a 3x. So this is going to be 3 pi fourths plus k pi, and then I'm going to divide by 3. So this gives me x equals, if I divide everything by 3, that's going to be pi fourths plus k pi thirds. That's better because it's in terms of the variable we want, but we need to write down only the answers between 0 and 2 pi. So we're going to take that answer set that looks like this, and I'm going to plug in k equals 0 k equals 1, 2, 3, and so forth, until I get all the answers in that interval. So what's the first one? First one's what you get when you plug in a 0. If you plug in a 0, that's going to be pi fourths plus 0. So the first answer is pi fourths. Next answer, we're going to plug in a 1. So we've got pi fourths plus pi thirds. Pi fourths plus pi thirds. Pi fourths plus pi thirds. Got to get a common denominator. So that's going to be 3 pi twelfths plus 4 pi twelfths. So that's going to be 7 pi twelfths. That's the next one. How do we get the next one? Plug in a 2, right? We plugged in 0, we plugged in 1, let's plug in a 2. So this is going to be pi fourths plus 2 pi thirds. Same thing, got to get a common denominator. So this is going to be, again, 3 pi twelfths plus 8 pi twelfths. Add those together, 11 pi twelfths, right? Okay. There are two things that you could do here. Does anybody spot a pattern at this point? Tristan spots a pattern. Michael spots a pattern. Anybody else? Jason spots a pattern. Alec? Mason? Corey, what's the pattern? Increases, let's see, did we get this right? 2 pi thirds. Got that right? Yeah, because, I mean, if you just counted the top, that's not quite right. You've got to have these in terms of twelfths. This would be 3 pi twelfths, so that would be another 4 pi twelfths, another 4 pi twelfths. So the next one would be another 4 pi twelfths, so that's going to be 15 pi twelfths. Okay, we could do that, or see this mess that I made right here? Each time I had to get a common denominator. It might be a lot better if I went through and said, you know what? If I'm going to have to combine these, let's write it this way. Let's write them in terms of twelfths already. So this is going to be 3 pi twelfths plus k times 4 pi twelfths. So plug in a 0, there's 3 pi twelfths or pi fourths. Plug in a 1. There's 3 plus 4, there's our 7. We don't even need to worry about the denominator at this point. Okay? Plug in a 3, that's going to be 12, plus that's going to be 15. There's our answer right there. Okay, let's keep going. So if we just keep adding 4, this is going to be 19 pi twelfths. This is going to be 23 pi twelfths. And the next one's going to be 27 pi twelfths, right? 27 pi twelfths. What's wrong with that? It's bigger than 2 pi. Okay, 24 pi twelfths would be 2 pi, so we're not going to include that one. So we get those 6 answers there. Okay, are there any questions? Easy enough? Okay. Why does it repeat every pi thirds? Why do those answers repeat every pi thirds? Ryan?
Because that's how, because you take the x equals pi fourths plus k pi thirds, and you sort of plug in how many times you want k to, is how many times you go.
Like how many times it takes to go around or something like that? Yep. Ty?
It goes 3 times as fast.
That's it. This right here, that's all that 3 does, is it makes it cycle 3 times faster, so it's going to produce answers 3 times faster. If it normally produces an answer every pi, it's going to produce an answer every pi thirds. You just tell it where to start. Does that make sense? Okay, let's look at the next page. Okay, would you try that one, please? And do we get more answers or fewer answers than we typically get on this one? And if you know the answer, then you'd want to think about why. Does this start off any different than any of the other problems we've done? No. Use substitution. So, whoops. We're substituting for the x over 2. So if we substitute for the x over 2, this just becomes a nice easy equation. Sine of u equals radical 3 over 2. And remember, I said it's better to write down the answer sets and then figure out the answers in the interval you need. So on this problem right here, if we draw a picture of this, we need a radical 3 over 2 for the y coordinate on the unit circle, or we need a radical 3 for the opposite and a 2 for the hypotenuse. So this is going to be radical 3, this is going to be 2. I recognize that triangle, that's a 30, 60, 90. So this answer right here is 60 degrees. That's my reference angle and my reference triangle. And then I've got another one over here, radical 3, and that's a 2. That's a negative 1. Again, that doesn't matter. That makes this a 60-degree reference angle. So if I wanted to figure out what the answer is, again, sticking with that whole x-axis idea, if you're still struggling with, okay, I've got this answer, especially if it's on the calculator, how do I figure out the other ones? Take that and figure out where we are on the x-axis. Right here, this would be 180 degrees, and we need to back up, so we need to subtract 60 degrees. So that's going to be 120, okay? So sorry to belabor the point, but those are our starting points, and each one of those repeat every 360 degrees. So we have u equals 60 degrees plus 360k, and we've got u equals 120 plus 360k. Okay, now I reverse the substitution. X over 2 is equal to this stuff. So that's going to be 60 plus 360k. And I'm going to do the work for this. I'm going to multiply both sides by 2. So this is going to be x equals, this would be 120 plus, well, if I multiply 360 by 2, I get 720. So there's one answer set. But they told us they want answers in a specific interval, so this is going to help me get those answers. Okay, I do the same thing here, okay, but I'm going to do the work a little more quickly. This is going to give me x equals 240 plus 720k. Again, answer sets. So let's plug in k equals 0. Notice this is a positive interval. It's from 0 to 300, or 0 to 180. That's 3 full circles. That's going around the unit circle 3 times. So if we plug in k equals 0, I'd get 120 from this one, and I'd get 240 from this one. Those are definitely within our interval. Let's plug in k equals 1. That's going to be 720 plus 120, so that's going to be 840. Is that right? 840 degrees for that one. Okay, plug in k equals 1. That's 240. 720. So 240 plus 720, 960. We good there? Oops. Make that look right. 960. Okay, and then let's plug in k equals 2. If I plug in k equals 2, what do I get out of this right here? 1440 plus 120. It's already too big. Same thing will happen here. So I can stop right there. I don't need to go any further. Those are the 4 answers to this problem that fit in that interval. This is going around the circle 3 times. Normally we'd get, like at least 6 answers. Why do we only get 4 answers on this one? Ryan?
Because it's you divide by 2, which means it makes it longer.
Yep, it increases the period. It slows down the cycling, increasing the period. That means we get fewer answers than we'd normally get. On the front page, we always got more answers. Here we're getting less. Going around 3 times, we only get 4 answers, okay? Rather than the 6 or the 12 or however many we'd normally get. Any questions there? Okay, again, this is a silly example to use this on, but it does illustrate the point. Remember, we're always comparing ourselves to the x-axis. So if you get an answer that's something like this, let's say this answer over here is 0.73, and there's another answer over here. Okay, this is in radians, by the way, right? How would you figure this one out? What's the x-axis in radians over here? Pi, and we need to back up, so we're going to do pi plus or minus. minus 0.73. That's how you'd figure those out. Okay, and then they'd repeat every 360 degrees or 2 pi or whatever it happens to be. Good there? Okay. All right, let's take a look at the interesting example. There's an example in your textbook that's similar to this, not nearly as creative though. Okay, and you also have some problems in your textbook toward the end. I believe you have 2 on your assignment like this. All we're going to do is just brush on why these equations work the way they do, what stuff you'd plug in, and then we're actually going to go through and we're going to solve one. Okay? So there are these 3 equations that you're going to need to solve these couple of problems in your textbook and this problem right here. So the first one is this one right here. It relates the distance traveled by a projectile as it relates to the velocity that it was launched with, so the initial velocity, and the angle that it was launched at. So here's the angle that it was launched at. Notice that it's been doubled. Okay? And then this is the initial velocity. So V naught, V with that little subscript of 0, that's how you say that, V naught. And then D is the distance. Okay? This is measured in feet. Okay, we normally measure that in radians, but I suppose if you wanted to do it in degrees, that's not that big a deal. Okay? And then the velocity, I believe, is measured in feet per second. Okay? And then we can also keep track of the positive x and y coordinates. So it's kind of like we're launching things into the first quadrant with v naught, t, and cosine of the angle. That'll tell us the x coordinate of wherever the projectile is. And then the y coordinate is given by this one right here. Those of you that have had physics, this stuff shouldn't look too unfamiliar, especially the minus 16t squared. Okay? All right, any questions there? So this relates the velocity, the angle, and the distance that it travels. Okay, so when you launch it, how far does it go? What is this distance right here? Okay, if it had that initial launch angle, I guess they're using theta, and that initial velocity. And this tells you what the x coordinate is, where is it horizontally, and this tells you where is it vertically. It tells you the y coordinate. Okay, any questions? Okay, let's do the problem then. Everybody's played Angry Birds, right? Okay, a little too much. Okay, an angry bird is to be launched with an initial velocity of 90 feet per second at a pig located 100 feet away. Assume the pig is at the same height as the bird and use the equations above to find the 2 possible launch angles. Then for each of the angles, compute how long the bird is in the air before he destroys the pig. Okay? Now, whether you know anything about trigonometry, physics, or projectiles or anything like that, it doesn't take very long playing Angry Birds. You can get a 3-year-old to figure this out. If I want this bird to hit that pig, there are 2 ways to do it, aren't there? Okay, one way is to launch it like this, so that it goes like that and hits a little more directly, kind of a very low trajectory. And the other way, depending on the obstacles in the way and all that sort of stuff, might be to launch it so that it goes up and then comes down and hits it like that. Those are the 2 options. Okay, now figuring out what those are, that's the tough part. Okay, now on Angry Birds, you've got the reset button, you've got an endless number of tries. So it's pretty easy to say, you know what, I went a little too high last time and it dropped short, so I need to change my angle a little bit. Or it was way too low and it landed before the pig, so I can adjust it. Okay, we're going to figure out exactly the angles that we can launch this at. Okay, so here's how we're going to do it. We're going to use those equations up above in order to figure this out. So, this is what we know. We know it's 100 feet away, and we know we're going to launch it at 90 feet per second. Okay, that's the stuff in the problem. Well, of these 3 equations, I just gave you 2 variables, and you can figure out the other one. Okay, and given the fact that we've been discussing it, okay, that's the distance, that's the initial velocity. What were we trying to figure out? The angle. We're trying to figure out the launch angle. Well, am I going to use 1, 2, or 3? A couple of us have some idea. The suggestion is 1. It is 1. That's the first thing we need to figure out. Because if you don't know the launch angle, you can't figure out its x and y coordinates. So here's what we're going to do. It is v naught squared sine of 2 theta equals 32 times d. So grab your calculators. We're going to solve this problem right here, and we'll figure out the launch angle for the pig. So this is going to be 90 squared sine of 2 times theta equals 32 times the distance is 100 feet. So this is going to be the sine of 2 theta equals 3200 divided by, this would be 8100. So I can really cancel those off. I can't cancel 32 and 81, so I'm going to stick with this. This is the equation that I'm solving. Right? What do I do now? Yeah.
Where did the 8100?
90 squared is 8100. Okay. Any questions? What's my next step? Substitution. I'm going to say wherever there's a 2 theta, I'm going to put a u so I can make it as simple as solving this one right here. The sine of theta is equal to 32 over 81. Now, listen very carefully. A lot of people make this mistake. They say, well, you know what? Why do you need to bother doing that? This would be pretty easy. The only possible answer would be in the first quadrant. Okay? It is a multiple angle equation, and you have to be really, really careful about making assumptions like that. Okay? Just because the answer to this part of the problem has a shooting over here, okay, once we compensate for that 2, it might end up shooting in the right direction. So keep that in mind. So we're going to solve this problem right here. Is this something we're going to draw? I suppose you could. It certainly can't hurt. 32 for an opposite side, 81 for a hypotenuse. So I'm going to do 32 here, 81 here. Certainly not a triangle that looks familiar. Put your calculator in degree mode. Okay, so we've got some sense of how big this angle is. Should be decent size. And what is the sine inverse of 32 over 81? Okay, so this is 23.27. You might want to write out several decimal places, maybe 3, 4, 5, something like that, to have plenty of accuracy. Okay, is there another angle that has exactly the same sine ratio? Yeah, it looks like it's pointed over here. So this is 32, this is 81. If this is 180 degrees, we need to back off exactly that much. So we're going to do 180 minus 23.27. So the other answer is 156 point what? 73. Okay. Now I could say that each one of those repeat every 360 degrees. Okay, but that's going to put it way outside the range that we want. So we're going to do these two answers. U equals 23.27 degrees and U equals 156.73. Now, are those the answers to the problem? No, for two reasons. This one, that looks like a reasonable answer, but there's no way this one is because it's pointing off the other way. We'd be launching the bird backward at that point. But since the problem was originally about thetas, now let's replace the variable. So this would be 2 theta equals 23.27, and this would be 2 theta equals 156.73. And then we figure out what theta is. What's theta for this guy? 11 point what? 11.635? Is that right? Okay, and what's theta for this one? 78 point what? 365. Okay, any questions? Okay, isn't this about what we'd expect if we were playing Angry Birds for real? Okay, wouldn't you expect one of the answers to be a low trajectory, like about 11 degrees, maybe something like that, and then the other one to be way up here, like at 78 degrees? Or 78 degrees. Okay. Any questions? What's that? Absolutely. Okay. If you can set this up again, you have no idea how much work it took to get this picture. Okay. Is that the answer to this particular problem? It's part of it. It says find the two possible launch angles. So we've got that part taken care of, but it also wants us to figure something out. It wants us to figure out how long is each one of them in the air. Okay, definitely that lower trajectory is going to get there faster. It's not going to be in the air as long. Okay, Well, let's see. How do you do that? Okay, you could solve either number 1 or number 2. We know the angle. We know the distance. So we could put 100 in for this. We know the initial velocity. We don't know the time. We do know the cosine of the two angles. So we're going to have theta be 11.63 and theta be 78.365. That would solve it for us. Could we do this one? You could. It's a little more pain in the butt. What would I have to plug in for y? You'd have to plug in 0 because that's when they're at the same height. Our reference point would be 0. So this would be negative 16t squared plus 90t times the sine of theta. Again, we'd plug each theta in there and solve that. By far, this one's easier, so let's use that one. Okay? So we'll plug this stuff into the problem. This is going to be 100 equals 90t cosine of 11.635. So that means t is going to equal 100 over 90 times cosine of 11.635. Type that into your calculator, and what does that say? Anyone? Dallas? Did you get that? The answer in seconds? You're too busy dropping pencils to see how fast they drop?
Isn't it
9.9? Meters per second squared. Yeah. Okay, anybody get that? And then the second one, the only thing that you'd need to change is change that to cosine of 78.365. Make sure you're in degree mode and make sure the denominator is in parentheses. You're this good at texting and you can't punch buttons fast enough to... 1.13 seconds for this one. And what about the other one? 5.51. Okay? Okay, again, both of those in seconds. You've got a problem like that on your assignment, except for it's not Angry Birds. It's not nearly as cool as that. It's some medieval catapult throwing a flaming hay bale over a wall. And you have to figure out which angle will make it over the wall, and then how far it clears the wall or something like that.
That's awesome.
Okay, we'll learn about parametrics. That'll make it a little bit easier to do in the next chapter. And then you've got another one about Ken Griffey Jr. throwing a ball from the outfield to home plate. So there you go. All right, last two problems. 5.51 seconds. Again, the key here is to make sure you put the denominator in parentheses and make sure your calculator's in radian mode. You could do the whole thing, degree mode. You could do it all in radian mode if you wanted to. Okay. Any questions? Okay. Grab your calculator again if you haven't already. On this one it says solve these equations. So we've got an x squared equals cosine of x. So that's something that looks like this, crossing with something that looks like this. It's only going to cross in those two places. So literally all you have to do is put your calculator in the right mode and graph the two of these and find out where they cross. So I'm in radian mode. Could you do this problem in degree mode? Okay, Alex says yes, you could do it in degree mode. Anybody say no? You can't, because degrees squared wouldn't make any sense. Okay? All right. So let's put these in here. So I'm going to put in x squared for one graph. I'm going to put in cosine x for the other graph. And then I'm going to hit zoom. And the decimal window is a good one to start on this one, especially because we know these are fairly small. We're looking for that point and that point. Can anybody tell me something about those 2 points? They are the same as far as the x coordinate, except for the sign. And the y coordinate is exactly the same. Okay? These are both, what do we call these functions that are symmetric about the y-axis? They are reflections across the y-axis. They have symmetry across the y-axis. We call them, seriously? Even. Thank you very much. Okay, those are called even functions. So again, if you forgot how to do that, You hit second trace. We want to know where they intersect. So it says first curve, and we just hit enter to say yes. Yes, I want that parabola. Yes, I want that cosine. And then it says take a guess. You don't need to be perfect. You just need to get on one side or the other. It's going to find this one right here, and it's going to say the intersection is 0.824, and the y-coordinate is 0.679. Any questions? What's that? Yep, you hit second calculate. We want to find an intersection, so I'm going to hit 5. It says first curve, second curve, and all I have to do is, when I guess, I just get closer over to there. So if I just get on that side right there, it's going to find the one over there. Good. It's the same thing, it's just the negative like we talked about. Any questions? Okay. Let's see, for the next section, I'd like you to solve this. So I already had you practice a little bit of this last time. I'd like you to solve this one, and then figure out what would happen if I told you u is equal to sine of x. Okay? Please solve that before you come next time. Remember, let's see, so we've got no class tomorrow. I'm going to cover 4-4 on Wednesday. We'll be done with 4-4 on Wednesday, and our goal is to get out of here with no homework over spring break, right?
Yes.
So that means Thursday in office hours, you want to leave office hours with maybe nearly everything done, maybe 1 or 2 problems left. We'll correct 4-1 next time and 4-2. Or did we already correct 4-1? Okay, we'll correct 4-2 on Wednesday. Please try and have 4-3 done.
That's my 4-1. I was gone on Friday, so people see a picture of the jobs.